Hi, for this lecture, we will look into relations and closure for a grammar as well as simple grammar. Okay, let's look into the definitions of closure, relation and closure. So the closure of relation R, okay, with respect to property P is the relation obtained by adding the minimum number of ordered pair to R to obtain property P. Okay, so in this case, R is a relation. Normally, relation will be in ordered pair. For example, we have R contain A, B. This is what we call as ordered pair. They have A and B, or we have B and C, means that in pair. Okay. It can have more element for each of the relation. We can add another element to this relation. So this is what we call as a relation of ordered pair. Okay. And we have what we call as a property. Property can be symmetric, can be reflexive, can be transitive. That is what we call as a property. So in this case, we want to find a closure for these relations. Okay. Normally, relation will be in the forms of list of ordered pair element. So what does it mean by closure is how we want to add another element to make it fulfill the requirement for each property. For example, we want to make the relation R to be reflexive. So what are the ordered pair element that we need to add in order to make that relation R reflexive? Okay, so if R is a relation, then reflexive transitive closure of R is designated by R star. So this R star indicate closure for relation R. So we write it using a star. We represent it using a star. Star represent closure for relations R. Okay. There are three types of properties, and of course there will be three types of closure as well. So we have a reflexive, symmetric, and transitive. But for this lecture, we will look into reflexive and transitive closure. Okay, what does it mean by reflexive and transitive? Okay, so look at this. Number one, all pairs of R are also in R. So this is how we find the closure. Okay, so for the closure, what are the elements for closure? First, we need to write all pair of R. Means that we need to list all elements in R. Okay, that is the first step. For example, your R contain A, B and a B, C. So you write that down as a closure as well if you're being asked for the closure. Okay, and then the second rule is if A, B and B, C are in R closure, then A, C is in R closure as well. So this is what we call as a transitive. So transitive, what does it mean is if you have an element from A to B, okay, which is the first one, and you have B to C, so the closure will be the transitive closure is A, C. This is what it means by the second rules here. Okay, that is a transitive. Okay, so for this relation R to be a transitive closure, so we add here A, C. Okay, so this is transitive closure. Okay. Okay, number three, if A is in one of the pair of R, then AA is in R. So this is reflexive. So means that if you have A inside your relations, so you need also to have AA. And then if you have B, then you need also to have B. and then another element here is C, then you need to add another element C. That is a reflexive. If you done a metric table, okay, a metric table, if you look into a metric table, let's say you have here A, B, C, A, B, C. So what does it mean here? If you have a reflexive would be, if you have element A, B, C, you need to have a diagonal B, and C must be exist. Means that the diagonal here must be exist. That is reflexive. Reflexive, you look into the diagonal line in your metric table. Means that for reflexive, you need to have all your diagonal line must be 1. If you have another element D here, D means that you need to add another 1 for D as well. Means that you need to have D as your ordered pair in your relations. Okay, that is for reflexive. Okay, so reflexive actually is adding loop and a transition is adding a new arc. So what does it mean? Actually, if you have this particular graph, okay, reflexive, actually you're adding a like this, adding a loop to your graph. While transitive, actually you're adding another arc, means that another arrow, that is transitive. Okay, all right, so let's move into an example to see the closure. Okay, relation closure. Show that R1 closure with the reflexive transitive closure, okay, of relation R1. So given that this is your R1, okay, R1 contain A, B, C, D, B, A, B, C, and C, C. Okay, so how to write the closure? First, according to the first rules, you need to list all the elements for R1. So this is all from R1. Okay, this is all from R1. Okay, this is the first step. Second step is to look into transitive. Okay, from this relation, what would be the transitive closure? Okay, if you look into R1, you need to list all possible transitive arc for relation R1. Okay, for a better understanding, let's draw a graph diagram for these relations. So you have A to B, okay, and you have B, A to B, you have B to A, okay, and you have C, let's look into B to C, B to C, okay, this is this one. Then you have C to D, C to D, this one, and C, and C goes to C itself. Okay, so this is the diagram. Okay, for transitive, it says that when you have A to B, B to C, you need to have one A to C as a transitive. Okay, you can see here, you have A to B, B to C, then the transitive closure will be A to C. Okay, so that is the first one. Okay, next one, another transitive closure is you start from B, you have B to C, C to D, so the transitive will be B, D. Means that there is a way. If you have a way from B to C and another way from C to D, means that you can go from B to D. That is transitive. Okay, second one. And the third one here, AD. Okay, so means that you have A to B, B to C, C to D. So there must be another way directly from A to D. Okay, so this is transitive. Okay, now let's look into a reflexive. Okay, reflexive say that you're adding a loop to each of the element uh, inside the relations. Okay, if you look into the relation here, you have A, you have a B, you have a C, and D. So you need to add a loop for each of these. Okay, if you look into the diagram, the loop here, the original R1 will have CC. Okay, CC. Okay, I change the color. Okay, CC. Okay, you already have CC. Now you left with AA, BB, and GT. So this is reflexive closure of it. So the R closure will contain all of this. This is reflexive transitive closure for this example. Now we look into a simple grammars. Okay, we want to know what is a simple grammars. Okay, by definition, a grammar is a simple grammar if every rule is of the form A goes to A alpha. So this is the representations of a simple grammar. Okay, so A, the big A here, capital letter A is a non-terminal. A small letter A is terminal. Okay, so A represents non-terminal. A small letter A is any terminal, and alpha represent any string of terminals and non-terminals, any string. Okay, so that is alpha. So must be in that form. Okay, a simple grammar also, and every pair of the rules defining the same non-terminal begin with different terminals on the right side of the arrow. So what does it mean is, if you have a non-terminal A, goes to A, B, for example, and you have another rules start from A as well and goes to a B, like that, B terminal. Okay, then so this is what it means every pair. This is a pair. The first rule also start with A, a second rule also start with A with the same non-terminal, and for it to be a simple grammar, both of these rules must start with a different terminal. So this is start from A, this start from B. Different terminal. Only then it is considered as a simple grammar. If it is example like this, A, the first A goes to A, B, and the second rule A goes to A. So this is not considered as a simple grammar because both of these non-terminal rules, A, the same non-terminal rules, start or begin with the same terminal, which is A and A. So this is not a simple grammar. So this is a simple grammar. So that is a definitions of simple grammar. Okay, now looks into this example. We have a grammar 9, grammar 10, and grammar 11. Okay. The first one, it says the grammar G9 below is it's not below, it's on top here, is simple, but the grammar G10 is not simple because it contains an epsilon rules. Okay, so G9 here is simple because it has the same non-terminal rules. Both of it is start from S, but it begins with a different terminal. The first rule begin with A, the second rules begin with B. So this is simple grammar. While in G10, the first rule start with A, the second one start with epsilon. Epsilon is not considered as a terminal in this case. Okay, so this is not simple. Okay, the grammar G11 is not simple because two rules defining S begin with the same terminal. So the two rules defining S. So this the first rule S, the second rule also start with S, but it begin with the same terminal. So this is not simple. Okay, so G10 is not, G9 is simple grammar. So understand that? So this is a simple grammar, definition for simple grammar. Now we look into another term in a grammar that you need to understand, which is selection set. Okay, so what is selection set? The definition here given that the set of input symbol, which is terminal symbol, which imply the applications of grammar rules. Okay, what does it mean here? Okay, for a simple grammar, the selection set of each rule always contain exactly one terminal symbol, the one beginning the right hand side. So this is the beginning, the right hand side. So this is the left hand side. So the one beginning is the first element after the arrow. Okay. So in grammar G9, the selection set of the first rule is A, and the selection set of the second rule is B. Okay. So to determine the selection set, normally we look into the first string after the arrow, means that the first string on the right side of the grammar. So in this case, on G9, the first rule, the selection set for the first rule is A, while for the second rule it is B. Okay, always remember the selection set is the first terminal on the right hand side. Okay, so that is how you look into selection set for each of the rule inside the grammar. Okay, let's look into the example how to derive a tree from the selection rules, selection sets, I mean. Okay, for example, you want, using this grammar G12, you want to derive A, B, B, A, D, D, D. This is the string that you want to derive from G2. So how to derive a derivation tree from these rules? Okay. The first string that you want to derive is A. Okay, so we normally start with S for derivations. So look into the rules here. First rule, second rules, and the third rule here. Which of the rules start from A? Because the first string that you want is A. So using the selection, okay, if you look into this grammar, the first rule, the selection set will be A. The second rule, the selection set will be B. The third rule, the selection set is D. Okay. Now you want to derive A first. From these three rules, which of the rules that have selection set A? It is the first one. So you start with A. Sorry. So you start with choosing the first rule. Okay. Normally we have difficulty to choose which rule to start first. So we look into the selection set. So now we choose first rules. Okay. So S goes to A, B, S, D. So it's come from the right hand side of the rule A, B, S, D. Okay. Now we're done with A. Now the next one is B. If you look into the first rules here, we already have AB here. AB, okay? So actually we're also done with B. Now the next string we want to derive is B, okay? So B. So the selection set that contain B is rule number 2. So we go for rule number 2. So we already have AB. So the next non-terminal S, we should instantiate it from second rules, which is B, A, S, D. Okay. Now you already have AB. and BA. Okay, so we cross B and cross A as well. So next non-terminal here is S. So which rules that we want to use for the next derivations? So it depends on the next input, next string that we want to. The next string is D. So we look into this rule. Which of this rule actually have D as the selection set? So we look into this rule that have number 3, rules number 3, which have D for the selection set. So we derive, we instantiate the S with D. Say for rule number 3, we instantiate this S with D. Okay, we instantiate this S with D. So now we have AB, BA, D, and we have no more non-terminal here. So no more derivations. So we have a D terminal and another D terminal. So we can get ABB, ADD from this grammar using the selection set that we have here. So that is the purpose of selection set, is to determine which rule that we need to instantiate first. Okay. Okay, now we look into how we want to pass this simple grammar. Okay, we can pass this simple grammar language with a push down machine and also a recursive. This is an and recursive descent parser. Okay, there are two ways. Okay, now first we want to look into how we want to do a parsing simple language with a push down machine. Okay, given the grammar G13, okay, we have 4 rules there. We want to use a push down machine to parse this simple language. Okay, first we need to construct a push down machine table. Okay, how to construct a push down machine table? We normally need to look into what is the stack symbol, stack input symbol, and also what is the input symbol. So there are two, stack symbol and input symbol. Okay. So normally for the table, we need, for in this case, the input symbol will be A, B, and also the N marker. Okay. And the stack symbol in this case is S. We have a B as well. Okay. Then we need to have A, B, and the starting point for the stack. Okay. So let's draw the line first. Sorry if the line is not straight enough. Okay. Okay, so to start with constructing the push down machine, the first we can write here is accepting stack when it is the starting point here with the N marker. So this would mean accept. So you can write that first. Okay, and then we look into the grammar, look into each of the rules. Okay, so the rules here, the selection set is A, second one is B, the third one is A, and the fourth one is B. Okay, so this will be the input symbol that we need to consider. Okay, for the first rule, S goes to A as B, and the selection set is A. So what we need to do is the input A on S. We look into the selection set A. So what we need to do is, if for the first rule, so we write here, we replace B as A. Okay, then we retain. Okay, so why is it B as A instead of A as B? Because in the stack table, normally we do it first in, last out, in the reverse order. Okay, so we replace that and we retain. Okay, and let's look into the second rules. Okay, is B. Okay, it's on the B here, input symbol B on the S input stack symbol. So we replace B, okay, and retain. Okay, rule number C, the third rule is also A, input symbol A. Okay, so what we do here is replace A, retain. Rule number 4, doing the same thing, replace A, B, and B. Okay, and retain. Okay, done with that. Now we look into if it is the same symbol, okay, like here, A with A, then we need to pop. So we need to remove it from our stack and advance. Advance means that you move to another stack. The same thing with B as well. B with B, if you see B, input symbol B, and the top of the stack is also B, then we pop and advance. Okay, so that is the for the grammar R1 into R4, grammar rules 1 into 4. So the rest of the cell here is reject. Okay, all of this is reject. Okay, this is how you write the you construct a push down machine from the grammar. Okay, all right. Look into how we can do a language parsing using a push down machine that we have constructed. For example, in this case, the language is L goes to the language is A, B, A, for example. Okay, this is the language. We want to do a parsing using the push down machine that we have constructed. Okay, so this is the push down table that we have constructed. To start with a push down parsing, we start with the initial symbol, which is the triangle, and start to do the derivations from S, start symbol S. So in your stack, the first initial stack, you have S. Okay, so the first input string is A. So this is the input string A on a stack symbol S. So you in stack symbol S is here with the input string A. So you have replace B as A and retain. So you replace on the next stack symbol with the S here with B as A. So you write B as A in the stack and retain. Okay. Then if you look into on the top of this stack, you contain a string A. Okay, with the previous input symbol is A. Then we need to pop, means that we remove it. Remove, and then we advance. Advance means that move to another symbol here. So in the new stack here, it contains BS because A is already been popped up. Now we look into next input symbol, which is B. Okay. On the top of the stack is S and the input symbol is B. So now we look into S and the input symbol B, which is replace B and retain. So now we replace this S with B. Okay, and retain. And we look into on the top of the stack is B, which is we need to pop and advance. So we remove the B and advance to new stack. So the new stack contain only capital letter P. Okay. The next input symbol is A. So the input symbol A on the top of the stack is P. So you look into this second row and the first column. So replace A and return. So this B is replaced with A. Okay. Now we have reached at the end of the string. Okay, before that, we need to look into on the top of the stack is A with A. So we need to pop and advance. So the next stack will be empty because we already popped A just now. So now we already reached the end of the string. Okay, so this is the mark of end of the string. So the last stack here, in order to be in accepting mode, it must be empty. Okay, it must be empty and must only contain initial symbol, which is the triangle here. Then we say ABA is accepted in this using this push down machine. Now we look into a recursive descent parser for parsing language for a simple grammar. Okay, the parser is written using a traditional programming language such as Java or C++. So this parser is using a programming language to parse a string. Okay, can be a Java or can be a C++ programming or any other language. A method is written for each non-terminal in the grammar. So in order to represent the non-terminal in the programming language, the non-terminal will be the method. Means that if you have a non-terminal S, you need to create a method for that non-terminal. Okay, if you have two non-terminals starting with S, you will need only one method to represent it as well. Means that for each of the non-terminal, we'll have one method to represent. Okay, it handles non-terminal by calling the corresponding methods, and it handles terminals by reading another input symbol. So what does it mean? For each of the non-terminal will be represented using a method. Means that you need to create a method for each of the non-terminal. And for the terminal, it is actually your input string. Means that will be the input that you need to read in your code. Okay. Now let's look into the example. I have a grammar G13 that contains 4 rules here. Okay. So if you look into this grammar, you have 2 rules that start with a non-terminal S and 2 rules that start with a non-terminal B. So there will be one method for S, another method for B. Okay, so to start with the programming, normally you need to create a class. So in this case, they create a class called RDP. RDP is recursive descent parser. This is the class that you need to create. So the input symbol here, they declare is as char INP because the input symbol here is AB. AB. So they declare it as a char. Okay, this is the main program, the public main program to read the input symbol as well as to call the object, the RDP object. Okay, and it calls the RDP.parse. This is the method to start the parser. Okay, this is the method to start the parser. So what is parse function? The parse function will get the input. Okay, and it will call the start non-terminal. So it must be the program must determine which is the start symbol. In this grammar, normally we start with S. So we start with S. So if input is N, so it is an accepting stack. This is another method just to print to say that the input is accepted, or else it is rejected. Okay, so N is a input symbol. Okay, we already determined how to start with our grammar by reading the S symbol. Now under the S symbol, what we need to do is we need to create a method for S, because we want to know if we encounter S non-terminal, what we want to do. So in this code, it will determine what the program need to do if they reach S non-terminal. Okay, under method S, so if the input symbol is A, okay, for S here, they have two rules for S, the first rule and the second rules. So they need to cater this rule inside this method. Okay, so if the input is A, so input get int. This is a method to read the input. Okay, to read the input. Okay, read the input, and then do, after you have read input A, do method S, and then do method B. Okay, so that is what you do when you see method S. Okay, so that is the end of rule 1. Else, if the input is P, which means the second rules input is P, then get the input. Okay, so read the input here. Otherwise, reject. Means that if not A, if not B, then it should be rejected, because as we only accept A, B only. So that is method for S. Okay, now we want to look into B, because I said for each of the non-terminal must have their own method. So now we look into method for B. For B, there are two rules as well. Okay, if it is A, okay, if input is A, then we read the input. Okay, else if input is B, then you need to read the input, and then you need to do method B. Okay, then you need to do method B. Then if the input is A again, after you done method B, and if the input is A again, get the input. Otherwise, it will be rejected. That means that if its input is not A, it's B, then it will be rejected. Here, if the input is B, so it is rejected. Okay, if it is A, then we read the input. Okay, else it will be rejected. Means that other than A and B, it will be rejected. Okay, so that is the end of rule 4 here. So this is only for rule 3. Rule 3, because it only contains terminal, is quite simple. But if it is a mix of terminal and non-terminal, the code will be longer. But the code must be sequential. Follow the order of the right hand side of the grammar. Okay, so this is how write descent parser, a recursive descent parser. Why it's called recursive? If you see the code here, the method B, in this method, they call another method B here. Means that they can have again and again and again. They call B again and again and again. So that is why it called recursive. Okay. Okay, we have done all the rules on the G13. So the rest of it is just to print the output. Okay, if it is accept, then you print accept. If it is reject, then you print reject and terminate the parser. Okay, when reject, you need to terminate the parser. So this is the code to read the input, because when you read an input, you need exception handling. This is the exception handling for Java code. When you read input, you need to have exception handling just to control so that you can get the right input. Okay, because in this case there only one char. If you enter number, it will throw an exception errors. So this is for the last code. So this is the uh, recursive descent parser for a grammar. In this case, the example given is like a G13, how you can construct a Java programming for this grammar.